Good afternoon, I'm Oliver Gunasekara, I'm CEO and co-founder of NGcodec, and I'm going to talk for about 30 minutes on recent trends in live cloud encoding. So I think we all know that this market is big and it's growing quite rapidly. So if you look at the number of streams that people are watching each day, that's the graph here on the left, and then you look at the trend over the last few years to move to higher quality. There's more HD video, there's a bit of UHD and 4K, HDR, high frame rate. And then you look at some of the newer codecs that people are beginning to make use of, things like HEVC, VP9 and even AV1. These are far more complex than the H.264, between 5 and 10 times more complex. And so the net result is that the market is basically growing at about 50% per year. That's what, in aggregate, the industry is spending on encoding video. And so when you look at that cost, how is it made up? And we see it's actually made up of a bunch of things. Some of it is to do with the streaming costs, the actual bandwidth that you incur to deliver the video. Some of it is about the storage of the video, and then some of it is about your compute resources to actually process and package the video. And obviously, as an encoder vendor, we have an impact on all three of these. But one that is very, very passionate for us is really the compression efficiency. How good do we encode? And that has big impacts on both the bandwidth cost and the storage cost. And so I'll talk about that first, and then I'll talk a little bit about the encoding cost. So visual quality, it's ultimately what drives that bandwidth cost, that storage cost, but also the user experience. If you look at someone that's delivering a lot of video, if they're large, they're paying a CDN or an ISP to actually deliver that video. And that's typically some amount per gigabyte. And depending on how large they are and how many concurrent viewers, it can be very, very substantial. Secondly, as a consumer, we typically have finite data plans. So it depends in geography. In the US, we've kind of moved more to fixed quality and unlimited data, but big parts of the world have finite data plans. And when those plans get extinguished, people stop watching. So the compression can really impact that. And then the quality of the experience. If you have better compression, your videos will start sooner. There will be less likelihood of video stalls, of buffering. And so the compression really can have a big impact on the quality of experience. For instance, if you take an old codec that's not really optimized, say H.264, and compare it to a modern codec like HEVC using some of our technology, there could be a difference of 50% of the bit rate. And that could be the difference between watching SD or HD, especially when consumers watch at peak times and there's an ABR ladder and you'll basically be falling back in resolution and quality to meet the demands that the network can support. So it really, really matters. And I don't know if many of you are familiar with this Chinese company called Huya. They're actually very similar to Twitch. So Twitch streams a lot of live video, but Huya is the same, but in China. But because they're a public company on NASDAQ, we can read their financials. And actually, in their 6K form, they reported that they spent just in one quarter, 3 months of the year, over $25 million in delivering video. That was their cost. And that cost went up almost 67% over the previous year. And it went up because they're delivering more video and at higher quality and at higher bit rate. So, a 25% reduction of bit rate by using a better encoder can have a real material impact on the bottom line here. So let's look at the landscape for different encodings. So there are basically different technologies that you can use in the cloud to do encoding. Historically, nearly everybody has used CPUs, software encoding, X264, X265, and these use CPU instances. And CPUs are really good because they're very, very flexible. They can run any type of workload. They're relatively easy to develop for. But the downside is that they don't have that much performance relative. and that much power efficiency. So you're paying for that flexibility in the fact that the quality that you can deliver is not as good, especially for live. Now, a second area, so these are what we would call fixed instruction sets. So you basically have to write your algorithm targeting the architecture that is delivered. And you don't have the ability to change that architecture. You know, Intel, when they designed the CPU, they designed how the processor operated, what was the memory hierarchy that was there. And so you have to tailor your algorithm to the architecture that you're given. Now, the alternative is hardware encoding. And hardware encoding breaks into two types. There is programmable hardware, such called FPGA, Field Programmable Gate Array. It's programmable in the fact that, just like software, you can load a new image into it and it functions completely differently. And you can do that an unlimited number of times, and it takes sub-second to change it. So that's the nice advantage of programmability. But as you can see on these axes, it's not as efficient. It's definitely more programmable than this ASIC, which is fixed. You can't change it. It has the most power efficiency. But once it's there, you can maybe run some software on an embedded processor, but you can't fundamentally change its design. And so, you know, an FPGA is a kind of nice middle ground. It's programmable, it's flexible, and it's far more efficient, but not as easy to use as a CPU. And so when you talk about hardware encoders, they are fully customizable. We can change the hardware design to do anything we want, including new codecs. But the advantage of FPGAs is that we can do that in the field. With an ASIC, we have to commit a new chip, and it takes a long time. And so the fundamental difference here is that we can adjust the architecture to the algorithm, not the other way around. And we can use that to deliver more performance, to do much better compression. So what am I saying? What I'm saying here is that fundamentally, if you talk about live video, CPUs are too slow. You know, if you're familiar with X265 or the SVT encoder from Intel, they have a great number of presets. And what you're trading off on the presets is how efficient it is at compression, i.e. what bit rate for a given visual quality, versus how many frames per second or how many channels can I do? And you know, typically for live video, you need to run in the medium or fast preset, or you need to run in, say, M10 preset here, because you don't have enough cycles available in the CPU to achieve the frame rate. You can't do 60 frames a second of these lower presets, even though that would provide you the absolute best compression. And so that's a real problem, and that's why historically live streams have far worse quality than video on demand. Because on video on demand, you can take, you know, for an hour of video, you can take 24 hours to encode it. Doesn't really matter. Well, I say that, it matters because you pay, but the application can take as long as you need, or you could split that video and use 100 machines to encode it if it's not live. But if it's live, you have to live with these presets. And so, you know, why we basically fundamentally believe that software just can't keep up. And it's absolutely true with advanced codecs like HEVC and VP9, and even more so with AV1. The complexity of AV1 is so high that if you want to deliver really great compression efficiency, you're going to have to either move to non-live or hardware accelerated. And you know, the reason for this is that, you know, you cannot do brute force. You just don't have enough performance. And so, you know, what we do is we do a full RDO, or rate distortion optimization. It means that we can do very extensive searching, looking for all of the optimum paths. And there just isn't enough performance available in a generic CPU to be able to do that. And that basically means that you have to run at substantially higher bit rates for the same quality. Now, you know, one of our largest public customer is Twitch. And if you know Twitch, they actually stream more live video than YouTube and Facebook combined. And they adopted our encoding technology precisely because of the bitrate savings that hardware acceleration can provide. And so they are using our technology on top of Xilinx FPGAs in their private data centers to stream live video. And we actually authored a white paper with Google, Twitch, and our technical folks. And it's a bit of a long URL, but if you just Google, Twitch VP9 blog, I think it will come up. But it's a really good technical white paper that goes into a lot more details for why hardware encoders can perform substantially better than software encoders, especially for live content. And I don't have time to go into the details today, but I'd encourage you to read that. So I've said some certain things, so why don't I actually give a little example, because it's nothing better, I think, than actually showing. So I've got two clips here that I encoded with our encoder. These are live encoding, even though I don't have the actual encoder here, so I just have the files. So I'm going to start with, this is a 1080p 30 clip. So this was live encoded. I don't know if the projector is 1080p, but it is 1080p 30. What do you think the bit rate of this is? So this was encoded live with our encoder. It can encode 4K live, but this is 1080p 30. With our encoder.
What codec is that?
This is HEVC.
HEVC?
Yeah, or H.265. 2 meg. Any higher or lower? Remember, this is live. It wasn't done offline. We didn't use 1,000 or 100 machines. We just used one FPGA instance in the cloud.
So 30 frames.
This is 30 frames.
5 megs.
5 megs, okay. 2, 5. It's 1. So I don't believe any other technology on the planet can do this visual quality at 1 megabit.
That's live?
Yeah, live encoded. 1080p 30. Yeah.
When you say live, how much of local have we have? How much data is it?
It's about 1 second. Yeah, so our encoder is using the look ahead. It's got a very advanced scene change detection. We are actually doing some form of reordering. There is the concept of presentation order and encoder order for compression efficiency. We are using fundamentally all of the techniques. But I think at 1 megabit, it looks pretty decent. And this is HEVC.
Is that delivered to the end user?
Yeah. This is we're a final distribution encoder. So
With an ABR, you didn't use ABR?
Yeah, it would be delivered in an ABR ladder. So our encoder is a native ABR, so it can encode up to 32 streams in parallel. So you can typically encode all the renditions at the same time. But I just chose one here.
Okay.
But let me show you another. I've only got one more, and then that's it. Second demo is, So actually, I lied. that demo was 264, but it was 720p. I don't know which one. Oh, it's autoplay, yeah. So it switched. Okay. So let me switch. So now, so this one is the 265 at 1080p at 1. But the other thing I wanted to show you was the 264. So we've never shown our 264 encoder. This is a sneak peek. We've been working on it for a while, but this is the first time we're showing it. So what I've done here is show, this is now 720p, so it's lower resolution, but I kept the bit rate the same. This is also 1 megabit, 720p 30 with H.264 now, but with our H.264 encoder. Again, this product isn't yet mature. We have the algorithmic model. The FPGA work will come over the next number of months, so it will be mature around IBC timeframe. But we've decided to go back and take all of the learning that we have from developing HEVC, VP9, and AV1 and apply it onto 264. And I think 720p at 1 megabit for 264 is also pretty pretty challenging. Our encoders, when we benchmark them with the visual comparison, not VMAF, but visual, we believe we outperform the very slow or the M1 setting of the SVT encoders. So, on the VMAF, it's a little bit off, but still pretty low bit rates. And of course, an HD or we could go much lower as well. So let's just briefly, we started doing this stuff 2015, and we've constantly been evolving. I don't want to go into too much depth here. So, this is where we kind of benchmark with a range of content, and as you can see, we're about 20 to 25% lower than the software encoders, especially when configured for a live configuration. And basically, our encoder is performing as good as a file-based encoder, but it's doing it live. And our roadmap is to just continually improve. So we believe we can deliver at least a 10% improvement per year. And because it's an FPGA, there's no restriction. We can just upload a new design. So substantial VQ benefits coming. Today, most of the big public clouds have FPGA instances already available in the cloud. So, if you go to AWS or Alibaba or Baidu or YA or any of these, just as you can rent CPU instances or GPU instances, you can rent FPGA instances. And that's what we are using. And so from a workflow point of view, from a pricing point of view, it's very, very similar to using a CPU. Typically, we're used as a transcoder in the cloud. So same basic architecture that you would see in YouTube or Twitch. You'd have a contribution feed coming in, and then you would use the CPU and the FPGA together to provide the transcode workflow. So typically the CPU would do the demuxing, would do the audio, the remuxing, and the packaging. These are really good CPU tasks. And the heavy lifting, which would be the decoding, the scaling, and the encoder, would all be offloaded to the PCIe accelerator in the cloud. And that would then allow you to generate all of the renditions in parallel for an AVR use case, package it with Dash or HLS, and then push it out to your CDN for delivery. And we have a very simple FFmpeg integration as well as a C API. A little bit on our roadmap. So, last year we delivered 265 and VP9, and we were achieving a single density on an FPGA. What we've done over the last 6 to 9 months is now doubled that throughput. So we can now do 4K 30 on a single, or if we use 2 FPGAs together, 4K 60. Xilinx has a nice new FPGA that's already been announced, will start to sample this year, called the Versal family. So today we're using the Vertex family. This is a 16 nanometer FPGA. This new family will be in mass production next year, and it's a 7 nanometer part. That means it's super advanced. It's got a lot of processing. It's extremely low power. We believe it will be priced very aggressively. And with that architecture, we believe we can double the throughput again. And so this effectively lowers the encoding cost, whilst we're also going to be deploying 264 and AV1. You saw a sneak peek of our 264. Our AV1 we showed at NAB coming together. And so that's really for next year. And then at some point in the future, we are planning to harden this solution to actually make a dedicated cloud transcoder. Now, once you do that, you can basically do something like 72 times the density over our first generation. So massive cost saving, whilst you maintain all of the benefits of the compression efficiency. And of course, as a codec company, we want to support all popular codecs. And so, we're actively in development of these 4, but we're tracking VVC and AV2. And probably as those become mature, if we see demand, we will support them. And people with FPGAs will naturally be able to just update and get the latest codec without them having to change any of their infrastructure. So let's talk a bit now about TCO, so total cost of ownership. So if you look at an Intel Xeon E5 and you estimate how many channels, what is the cost of that server, what is the running cost, and it basically breaks down to about $800 per year if you amortize the cost of the server over 3 years. Of that $800, approximately 2/3 of the cost goes for the actual server, and 1/3 goes to the running cost, the power consumption and cooling of that. And this is all nominalized per HD channel, 1080p 60 channel. Now, we use this as the reference. So you're typically, if you're using X265 or X264, you're using the medium preset to do the encoding. Some people are considering to use the E3. Now, the E3 has the Intel QuickSync. It's a hardened hardware encoder inside the GPU, but it was originally designed for consumer, and so it has some pros and cons. The pros are that it's incredibly low cost. You can do lots of channels, the power consumption is quite low. So from a cost per channel, it's very attractive. But its big downside is that its compression efficiency is very poor. It's a consumer grade encoder. It doesn't have a look ahead. It has very simplistic rate control, or AQ, and it basically needs 45% higher bit rate than the software encoders. So it makes sense for the long tail, but if you're streaming lots of video, all the money you save on the encoding, you'll spend on the bandwidth, and you'll have a much worse experience. Many of your consumers in an ABR use case will be falling back to SD, where they could have been watching HD with a better encoder. So few people use it, but it is a low-cost solution that's out there. This is where we are today. This is the Xilinx FPGAs. We come in a little bit cheaper, even though we get paid. These are open source that we're comparing against. We charge a little bit for the use of our encoder, but still we're coming in about 2/3 the cost of the Intel platform. But where we really win is we're at least 20% lower bit rate for the same quality. So the more video that you stream, the more you save and you have a better user experience. So I would say it's really this bitrate saving that's driving, and this is nice to have. Next year, we'll deliver our technology on the 7nm Xilinx FPGAs, which they've already announced and will soon sample. And again, we think we can half the encoding cost by doubling the throughput using that more advanced FPGA. And so now the costs come down further, and because it's a year later, we have a roadmap of continuously improving the VQ and bringing it down further. Now finally, when we get round to making an ASIC, this will have a drastically lower cost, at least 6 times lower. And again, because another year later, we'll have even lower encoding costs and bit rates. So finally, I was just going to show you a 1-minute video from NAB. So hopefully there is sound here. Let's just refresh this page. YouTube wants to buffer the whole video, it looks like. I don't know why. The network is up. Okay, well, maybe we'll skip that. I think I have it. Okay, I don't know if we have sound coming out of the system. Is it coming out the laptop? How about I can just use my mic then. Let's do that. Sorry about this. Massive video issues already. Just play. That's not it. I don't know why it doesn't want to work, but you can watch it on our website. This was basically what we showed at NAB. So on the left here was an ABR ladder. So we were actually on this encoder box, actually generating the dash renditions in parallel. So we were encoding 8 different videos, including the 4K version. I don't know if it wants to. I don't know why it's, but yeah, it's on the website, so I don't know, YouTube for some reason did not want to play it. I have no idea why. Okay, so final slide. So conclusions. So the cloud video market is growing very, very rapidly. As I mentioned, something like 50% per compound annually. And it's mainly driven by the internet hyperscalers. They're the ones that are doing significantly more encoding than anybody else. And obviously, when you look at encoding, it's not just the bandwidth cost, but it's the compute cost. And the two have an interaction. So you've really got to factor the two together. Our premise is that CPUs are basically too slow for modern codecs. You are going to waste money if you use CPUs. You can do better compression and at lower cost by using FPGA instances. And what we are trying to do is to deliver the best quality experience as you might have for video on demand, but deliver it for live. And programmable hardware, specifically FPGAs, really makes that possible. These are hardware encoders, but they're programmable, so you can update and change them in the field. And obviously, there is finally a roadmap to an ASIC. So thanks a lot. I'll open for any questions if there are. Thank you.
I'm still curious, you talked about that right now, even in the public cloud, FPGA is available.
Yeah. Yeah, I had a slide on that. If I go back. Yeah, so these public clouds, including AWS, have FPGA instances available that you can use.
I think as you did the comparison, it's comparable to the CPU. It's not like much
Well, if it depends on the cloud. So some clouds, are charging them the same as the CPU. I think AWS, it's about $1.65, which is very similar to a C5 instance. But actually, it's very, in our view, overpriced because, the price should be the price of the silicon and the price of the power consumption. And we know for a fact that an FPGA is a lot less expensive than a high-end Intel CPU, a Xeon, and we know that it consumes a fraction of the power. So there is another partner that we're working with that is going to be launching some FPGA instances at drastically lower pricing than AWS.
I was always under the impression that for the same amount of computation power, FPGA is much more expensive. Of course, it offers some advantage things that it can really easily parallelize stuff.
Yeah. So I mean, if you look at something like an Intel Platinum 8180 Xeon CPU, its list price is about $10,000, right? I can buy a card with an FPGA on for $2,000. And that's the whole card. So
But how many gates is that? I'm not sure.
well, we can do the same number of channels as that Intel. In fact, we have more compute. We can do much better compression. If you use that Platinum 8180, if you want to do live video encoding, you have to use one of the very fast presets. So FPGAs are definitely lower cost and lower power. Yeah. Question? Yeah.
Excuse me, I'm quite new in streaming area, the streaming field itself. But the question is, let's imagine I have a piece of hardware, like a server in my data center.
Yeah.
And I have a choice, either three actually, CPU, FPGA,
Yeah.
and NVIDIA Quadro E5000. How would you compare the last two options, like FPGA and NVIDIA GPUs, in terms of costs for one piece of GPU or FPGA, and in terms of bitrate and...
Yeah, so the NVIDIA NV encoder is effectively an ASIC. It's it's inside the GPU, but it's dedicated logic. So it is an ASIC. And so, it will win on encoding cost, density, because it's a hardened solution. But you can't improve it. You get what you're given. And the result is that its compression efficiency, although getting better, is still 20% off what you can do with FPGAs or CPUs running very slow. So, if you care about encoding cost only, it will win. But if you want the best compression efficiency, the FPGA will win. So it's a little complex. It depends which codecs, what sequences, but our encoder, our HEVC encoder versus NVE Inc. is about a 20 to 25% lower bit rate for our encoder. But they can do more density because they're an ASIC.
I think when you say it's ASIC, you mean the dedicated encoder kind of chip inside it, but there's other generic GPU.
So GPU is an ASIC, right? Because the encoding is happening on the dedicated ASIC logic inside the GPU.
Well, if you say that's ASIC, then CPU is ASIC too. I mean, it cannot.
No, it's the encoding algorithm is running on an ASIC hardware.
Right, that's a one kind of GPU that they have dedicated encoding.
Every GPU has
But
dedicated.
there's also some other companies doing generic software, using OpenCL or whatever language.
I think that's died out. There used to be, but even Elemental that invented that has moved away to pure CPU. The problem is if you try to do a hybrid of using the CPU and the GPU, you lose all the benefits because the GPU is good at decision making. It's not good at decision making, it's good at number crunching. But you have to move all those decisions back to the CPU. So these days, I don't see that. In the past, yes. Today I see CPU, FPGA, and ASIC.
Okay, so you think that generic GPU approach basically it's a non-viable solution?
I think it's died. I don't know anyone that's still doing it. Yeah. think there was a question over here.
Is the TCO VQ Comparison chart?
Yeah.
You showed that. So this interesting. Could you talk more specifically, for example, if it's a 4K video, so these bit rates, efficiencies, which you show there, where would the reference be for 4K?
This would be approximately for 4K. So
the reference would be like how many megabits per second?
well, it depends on the source, right? Because, you know, we need to do content-aware encoding. So, you know, two clips, one with almost no motion and one with huge amount of motion, need vastly different bit rates. But this is averaged over a wide range of sequences.
Yeah, and so but if you were to give with something like 8 or 12 or 14 megabits per second,
So at NAB, we were showing live 4K 50 encoding at 4 megabits.
and with which encoding?
So on this platform, this is the platform we use today. So this data is actually for 1080p, this pricing. I think it says up here, yeah, 1080p 60 channel per year. So, you know, 4K is typically 4 times that if you're doing 4K 60. But, you know, with software, live software encoding, if you try to encode at 4 megabits 4K, it will look completely unusable. But with our encoder, I think it's actually practical to deploy.
And one quick question again. What's really differentiates or what's more challenging when you talk of, say, streaming as VOD versus live? What's the main difference?
It's the fact that if it's SVOD or VOD in any description, it doesn't matter how long the encoding takes, right? You could, that 1 hour of video, you could take a week to encode it. You could split the video and use 100 machines to encode the video. With live, you can't do that. You know, so with live, you've got to maintain the frame rate. And so there is a finite limit to how much parallelism you can do. And with software encoders, they use as many cores as available. But those cores don't have access to threads that are running on different cores. And so that means they lose compression efficiency. So actually, as we move to higher resolutions, hardware becomes even more appropriate. You know, live 4K at 4 megabits, impossible to do with software encoders.
Live 4K 60
We were showing 4K 50, yeah.
and 4 megabits.
Yeah, yeah. Yeah, at NAB, that's what we were showing. Whilst at the same time, we were generating the 720p, the 1080p, the 480, the 240. All of that was being encoded at the same time on this one FPGA card.
One FPGA card, how many?
There are 2 FPGAs in that card.
Okay.
Yeah.
Is HD basically on its way out now completely?
No, I think HD will remain the mainstream for a while, but premium services are definitely moving up to 4K. Yeah.
So I remember maybe 1 or 2 years ago, I forgot, that Intel saying they have a roadmap to roll out some kind of hybrid CPU with FPGA on the same die. I didn't follow up with that.
Yeah, so we don't use Intel. Xilinx is one of our investors, so we only work on the Xilinx products. But from my understanding, that product has rolled out, but they put a relatively small amount of FPGA logic, and so it's not applicable for what we do. We need fairly large FPGAs. Yeah. Any further? Could try the video. I don't know. It is on our website. I don't know why YouTube decided it wanted to buffer it.
So I'm also curious that for the public cloud, they have those FPGAs available, and obviously they're not just only for video. This market is not high enough for them to make it so widespread available. What are they really
So it's the same question saying CPUs are only available for video or GPUs are only available. I mean, a public cloud puts the instance out and encourages any applications. But I would say video is probably the biggest workload, but there is some database acceleration, there's encryption, there's some genomics, there's a whole bunch of applications.
If there's a more application gen, it can keep the price down. This is a more
Yeah. Yeah, I mean, Twitch added FPGAs into their private data centers just to run video because they easily pay for themselves. Yeah. Any other questions? Or I don't know why YouTube doesn't want to play. I've been censored, maybe. I don't know. I guess we could try one other way. It is on our blog. Yeah. Resources, videos. Let's see if this plays. I don't know why YouTube doesn't like me today. Try restarting your device. Sorry, don't know why YouTube doesn't want to play it. Yeah. Okay, let's wrap. Unless there are any other questions. Okay, thanks.